Okay, so my name's Austin Dominguez, as some of you may know. I wanted to share about my summer here at SMCO, and I want to start with a little bit about myself. So I go to the University of Texas at San Antonio. I'm 21 years old, and I'm studying mechanical engineering. I was actually born in Detroit, but when I was 6, my parents moved me and my older brother back to Texas because the winters were too harsh, so they chose
They're still
heat.
too harsh.
They chose heat instead.
Tame now.
But yeah, I've heard that they're a lot more tame as of now. So I was raised in Corpus Christi, Texas, and I'm passionate about 3D modeling, process improvement, and I love the automotive industry. That's one of the foundations to me selecting GM for my internship. And below are some of the companies I've previously worked for. So I wanted to preface my study abroad in Japan, as some of you have maybe heard me talk about, and I wanted to bring that up. I went to 5 different engineering companies with my school, 2 of the top research universities. And I bring this up because I've always been really fascinated with Japanese engineering and a specific philosophy called Gemba Kaizen, which I'm sure most of you are familiar with. So Gemba loosely translates to the real place. And it's this idea that in order to find the solution to problems, you can't do it if you aren't where the problem is occurring. So the way I wanted to embody that this summer was I knew that if I was assigned an assignment, I wasn't going to find the solution behind my computer if it was out on the floor. I had to be out on the floor. And then Kaizen, as I'm sure all of you are familiar with, is the idea of continuous improvement, making improvements no matter how small and how gradual they are, constantly over time, is better than making none at all. And my inclusion message is inclusion works to the advantage of everyone. We all have things to learn and we all have something to teach. That's from Helen Henderson. And my safety message is for myself. We make cars, not people. There's only one of you, and asking for forgiveness and not permission never ends well with safety. And here's an overview of the assignments that I did. I had 4, with my main one being the first, and I wanted to go into detail about those now. So my first main assignment, which I got assigned very early on, was an EOAT for the HOPE project. So these lifting lugs were getting added to the shock tower, and I was assigned to design the gripper details that actually pick them up off of the bench, and the end-of-arm tooling in NX. And I had 3 main goals that I was able to achieve with my final design, which I wanted to go over with you guys now. The first was commonality for cost reduction. So we have 3 lugs in space that are randomly positioned based off of the shock tower, but in space they're all just sort of sitting. So I knew commonality would be important, so that way we could bring costs down, but I knew that if I made things common, it would help with my second goal, which was simplicity for ease of machining. So the 2 pieces that you see on the left are my final design, which get merged with the piece in the center for the gripper. And I know at face value it kind of just looks like simple lines and rectangles, but this is the accumulation of over 7 weeks of working with the tooling engineering team and learning the very important but minute details about how to actually make tooling and how to make tooling that works well on the floor. And for my third goal, I wanted to focus on industrial design for wear. And I did that with this small pad that you saw in the middle. Now, this pad's important because rather than having to remachine an entire finger, you can simply re-screw in a pad that's from a common vendor, which happens to be Grainger, and also relatively low cost in comparison to remanufacturing or machining an entire finger. And this is where I tie it back into the idea of continuous improvement. What you see at the end was this very simple set of rectangles, but that had very varied iterations over the course of my 10 weeks here, which I consider different shapes, sizes, and approaches to actually picking up this lug. And my end goal is sort of just the accumulation of those lessons learned and the embodiment of the idea of continuous improvement. And this is the actual end-of-arm tooling. There are some final tasks I need to take care of this week with Miss Jill with respect to a weldment file and final machining file, but as you can see in my first iteration, rough iteration on the left and final iteration on the right, like I said, simple rectangles, but infinite lessons learned in between, daily tweaks and improvements. And for my second assignment, I wanted to start by explaining it with an analogy. So if you thought about digging a hole and you were given a shovel from your boss, and that shovel, we'll call it shovel A, is capable of digging a hole 1 foot at a time, right? But the manufacturer says you can only use it about 100 times. That means theoretically in the ground you can only dig about 100 feet. Well, say you had your friend and he was using shovel B, same company, different manufacturer. That shovel can also only dig 1 foot at a time, but this one is rated for 500 holes. So you essentially get 500 feet in the ground, 5 times the total digging capacity. And then lastly, you have shovel C, same thing, 1 foot at a time, but you have 1,000 max holes that you can dig before the manufacturer says, this shovel is no good, you have to buy a new one. So these shovels sort of represent the tools that we use out on the floor. Different manufacturers, some even the same manufacturer, but different ratings. And so the question is why is shovel A such a lower rating between shovel B if the application is very similar? And I preface that because my assignment was essentially to find potential cost savings in low-performing, high-cost tools. And this is specifically done in the GAX machining department, and my tasks were to determine important tool variables, verify the actual data, so things like cutting speed, if it was saying something in a process sheet, making sure that that's what we were actually doing on the floor. And then, just like digging a hole, if you're looking at something like a drill over the course of its life cycle, determining the depth of cut, so how far it's actually drilling. And then, once we have all of that data, investigate the tool with the largest savings potential. And I started with the analogy, because at the end of the day, that's looking at process sheets and looking at CNC programming, verifying data, and generating an Excel sheet. And I knew that if I came to the presentation and said, this is what I did with my assignment, that wouldn't be as intuitive as just sort of demonstrating it physically. But I thought instead of going through the Excel sheet, maybe I'd give you an analogy on how I created it. So the first thing I did was I selected a tool group to study, and that was drills. We have a lot more drills than we have in any other group. So after I selected drills, I went ahead and gathered the data, which is, as you might think, going through the sheets and inputting it into an Excel sheet, and then calculating the length of cut. So to reiterate, a drill is going to drill a certain depth over the course of its life cycle. Then I worked with Shively to get the annual cost of what we spent last year on the drills that I listed out. I compared the performance, and then I chose an investigation for the tool I selected. And I wanted to go over a couple of these points more specifically. So here you can kind of see, just like with the depth that you can get in the ground with a shovel, there's a certain length of cut that you can get with a drill. And then that's the formula I used to determine it. And then for performance, after you gather all of your data, you can generate a graph that might look something like this. And there are a couple of important things that I wanted to point out with this data. So drill 10 on carriers is able to drill the quote-unquote furthest. If you thought about it, depth in ground, we're getting about 1,600 meters out of that drill. So it begs the question, why are all of these other drills, which you can see their depth in the darker blue, not able to achieve that? We have a very similar drill, drill 3 on tubes, able to achieve a very similar distance, but all of these drills in between are not able to. So inherently you'd think we'd go after the one that's the worst performing. Why isn't drill 8 able to get up to that 1,600? It's not even able to get a quarter of that. Well, I decided to investigate drill 19 because it's ironically the one we spend the most money on. And it's only getting about a quarter of that distance. And so my tool study is currently going on. For those of you that aren't directly familiar with what drill 19 does, it does feature 620 out of the carrier. It's the return lube channel. So it's an awkward drill. So I have a tool study going on right now, which is basically extending the life of the tool. And so far successful. We haven't broken any drills, and we're pushing the tool life to get to that 1,600. And here are some statistics. And that's the formula I use to calculate the actual savings potential. And while I'd love to say at the end of my 10 weeks I saved the plant millions of dollars or tens of thousands, I know that that 2,700 is important because it starts the conversations of we have all this hidden savings within the plant. Where else can we start having the conversation of how can we save money?
So you did not change the tool? You just ran the existing tool?
Just extending the tool life.
Okay.
Yep. And then monitoring it every day.
Yep.
And hasn't broken so far. And that's being done under the discretion of Mr. Keith.
Yep.
And so my third assignment is very similar to the one that I just described, except I'm looking at the saws and south finishing. It's very well known that they don't meet tool life. We've gone through a manufacturer change, which have been able to get them to be cheaper, but for whatever reason, they're still not even meeting half of the tool life they're rated for. So I had a very simple task, just investigate why they aren't. And those are the goals that I used to achieve that task. So I went out, created a very similar sheet, again, data on an Excel sheet, but this has some very important information like the counts in red are the actual dates where those saws were changed, and then I have notes and photos. And so the conclusion that I was able to draw from this, which is going to transition into an actual form of action, is that the saws that are getting changed prematurely are an Op 110, which we know is a tougher cut, and that's causing the carbide inserts to fly off. And the reason why these tools aren't meeting tool life is because there's no formal replacement procedure for these saws. So an operator will go in, if it's missing 4 to 5 carbide teeth, replace it, and then we basically have a wasted tool. Something that could have got full tool life is only getting about a third. And so this is undergoing further investigation by Mr. Keith to develop a formal replacement procedure. My last assignment, which was
So go back real quick. The 110 and the 120, are those identical blades? I think they are?
Yep.
Okay.
Yep, it's just 110 for both tubes and carriers is the more tough cut.
Yeah, did you compare, I wonder if the blade's not good enough for 110, can it go live in 120 for another, whatever? This is an easier cut, you know what I mean?
Yeah.
You didn't study that, I'm just asking the question.
If you look at like the actual like data that I have shown here, so like the first red box, that was changed after about under half of tool life, and then it was changed again because we had carbide inserts
The
that
changes
fell
are
off.
event driven, okay.
Yeah, so it's really hard to be able to correlate them directly. But the main correlation is that they're getting replaced because the carbide inserts are falling off. There's a few different reasons why they might be falling off. But either way, it's just up to the operator's discretion to say if these are falling off, we need to replace the blade, irregardless if it's creating a rough cut or not. And then my last assignment, which I did in the recent weeks, was set up a leak test fixture for the quality department, and then test some heads that we have. And so we had a high influx of left-hand heads that were failing due to leaks, and so we had this fixture that was on a pallet, very dirty, and so my goal was very simply to set it up, get it organized, and then start leak testing. And I was able to do that. I got it cleaned up, and I'm really good at testing left-hand heads now and finding where they leak. I've also been working with some people within quality to further investigate this. There was a Red X that was started about a year ago to investigate left-hand heads, and so what I've done is been able to find, I just got this done this morning, so I didn't want to fully include it in my slides, but find the actual origin position of the leak within the heads. And I've been gathering some data from the CUN number about things like temperature and the molds and the block that it's coming off of. And this is the last point that they were at the tree, which was make sure sand never gets into the mold, just remove the sand that's in the mold. So this is gonna get continued past me being here. So when I started my internship, I had a running list of things that I'd learned, but I thought like once I got to this point, it would be impossible for me to literally list all of the things I'd learned. So I chose like a few things, very practical things. Countersunk holes can be used as a locator in the absence of a dowel. That's really cool to me. I learned how to read CNC G code and position values and speed. I also learned, this was kind of early on, that issues can arise as far as 5 years into a product's life cycle. I know to many of you that might be obvious, but to me I thought that was pretty fascinating. And then I saw how here at SMCO we reduce waste by doing things like recycling coolant and metal chips. As I showed in my second and third assignment, how to evaluate CNC tooling for cost reduction. And then recently I learned you can design things in NX, but you need to make them manufacturable. So I learned about the usage of Z-pad, origin points, and probes to manufacture the tool assemblies. And then practically, I know it's a long list of things I've learned, but admitting you don't know how to do something is the first step of learning. In learning how, I thought I knew how to do a lot of things, but being here I really had to make sure that I put no ego into anything and make sure that I was open to new information, to things that I even thought I knew how to do. And then the fourth point, don't develop a good solution to a problem that doesn't exist. That basically is me saying, don't isolate your thought process too much, get other minds, consider things outside of the box, as the saying goes. And then General Motors has a big family feel environment. I learned that everyone's really here to help if you ask them. These are some of the trips that we went on. We went to the tech center a couple of times. I personally got to go to the Pontiac Engineering Center and see their research and development into fuel cells. I got to go to Milford with a different group. And so in the fall of 22, I spent an internship with Tesla. Last summer, I was with Flatiron, a heavy civil company, and they're making a new bridge in my hometown. And this summer, I was with General Motors, but I'm really passionate about fuel cell development in vehicles, so I hope in the future to continue to work with fuel cell. And for those of you that don't know, General Motors has a really long history with fuel cell that dates all the way back to 1965, where they manufactured this Electrobus. It was a concept vehicle, and it was General Motors' first fuel cell production vehicle. Had very low production, had 50 units, and only 12 sold. But General Motors has since made vehicles like the ZH2, which was for the federal government, the Army. It was a hydrogen-powered Colorado that they were using for vehicle testing. And so I wanted to create an individual list saying a thank you to everyone that has helped me, but I knew in some capacity and in some fashion, basically everyone in the plant has really contributed to my time here. So with that, thank you.